Okay, this is a lecture on time response of second order system. Okay, lecture on time response of second order system. Okay. Now, first of all, we will standardize the second order system. So now, already we have taken the problems on second order system. RLC circuit is a good example of second order system. Already I derived in the previous lecture. Directly I will write a transfer function. Otherwise, spring mass system is also second order system. Now, we know this, that is R, resistor, inductor and capacitor. So now this the input is what Vi of t and I of t and V naught of t. Okay, I know the in general or otherwise V naught of Laplace of output divided by Laplace of input is equal to 1 by LC S square plus RC S plus 1. The highest power of S is 2 in the denominator, so that I will call what? Second order system. So like this, if I take a spring mass system, this is a spring case stiffness, it's a damping coefficient, already I have covered. Okay, here there is a oil above and below, and here mass, here you are applying the force, input, the output is a displacement of the mass. Here also I can write the transfer function Laplace of output divided by Laplace of input equal to 1 by ms square, acceleration due to acceleration s square, plus velocity, the damping resistance is dependent on velocity, and k, it is only a function of displacement, so no s term. Already I have derived, I have find out the transfer function. Both are second order system. But how to make it generalized? You take many systems, a mechanical second order, electrical second order, something is chemical, but how to club, how to make a very generalized second order system. Okay, so now what I will do, the generalized system is, I'll make here, suppose 1 by LC divided by, if I make the S square coefficient is unity, R by L, yes, 1 by LC, correct? Suppose this is the V naught of S divided by Vi of S, and here also 1 by M, S square plus C by M, S plus K by M. Correct. Here also I have made a S square coefficient is unity. Fine. Now, how to make it generalized? Here I will write generalized second order transfer function, because you see here, you see the mechanical system, K by M is what? K by M is what? Omega n square. And C by M is what? 2 zeta omega m. So, in general I will write omega n square divided by S square plus 2 zeta omega ns plus omega n square. It's a generalized or standard form of second transfer function of closed loop transfer function of second order system. What is the closed loop transfer function of second order system? C of S divided by R of S equal to omega n square divided by S square plus 2 zeta omega ns plus omega n square. Okay, now we'll see what is zeta and what is omega n and what is omega d. Okay, fine. Now, here I have written natural frequency omega n in a mechanical is k by m. But in the electrical system you have seen what LCS square plus RCS plus LCS square plus RCS plus 1. So 1 by LC. So here omega n is equal to 1 by LC radian per second. To find the natural frequency of RLC circuit, to find the natural frequency of spring mass system. And zeta is what? Zeta is called opposition for motion. Opposition for motion. How to calculate the zeta? If I know C, so C is equal to 2 zeta omega n m. M equivalent or m. If I know C, I can find zeta. But the next question is, okay, in this case C has given in the problem, omega n means k by m and m is given. But how to calculate C? C, the problem will give the C, but how to find the C? C is a function of what? Suppose this is a piston and here cylinder. This is a clearance. Clearance is small clearance. This is very important. Okay, oil goes up and come down through this small clearance. Say small clearance is D. The area of cross section is A. Suppose this height is H and viscosity of the oil. So C is a function of, okay, mu, H, A and D. Some are directly proportional, some are inversely proportional. So I can calculate C if I know the viscosity is a very, very important factor in this case, and clearance also, and area of cross section. So the damping coefficient I can find C. This is C is called what? Damping coefficient. And already we know the what unit, Newton per meter per second, otherwise Newton second per meter. And zeta is called damping ratio. Zeta is called damping ratio. Okay, and right here zeta is equal to C by Cc. This is called what? Damping ratio. Unitless, Cc is called critically damping coefficient. C is damping coefficient. I already written. So Cc in a mechanical system, that is 2 root of mk, mass into stiffness. Mass into stiffness. Okay, see, indirectly omega n and zeta are very, very important in the second order. First order only the parameter is time constant capital T, but in the second order the two parameters, these are called zeta and omega, and entire behavior will change. If you change zeta, the output behavior will be changed. If you change omega n, the output will be changed. Both are, there are two important parameters. These are called zeta and omega n are called behavioral characteristics of second order system. So omega and zeta are very important. Okay, omega n you know root k by m. Otherwise, omega n how you are calculating? If it is a torsional system, this is a kT, this is a I, then omega n is equal to what? KT divided by I, radian per second. If it is a linear spring, then omega n is equal to root k by m. This kT is a torsional stiffness, and this is called torsional spring. Steel rod acts like a torsional spring. I is equal to half mr square. This is called what? Mass moment of inertia. Mass moment of inertia. Okay. Now I'll talk about zeta. Now, how the zeta, the types of zeta and all. Now, the types of zeta. So when the zeta is greater than 0 and less than 1, it is called under damping. And zeta is equal to 1, it is called critically damping. And zeta is greater than 1, less than infinity is called over damping. And zeta is equal to 0, it is called no damping or undamping. No damping or undamping. These are the actually three categories of zeta. 90% case I am using underdamping, some 5% critical damping, some 5% is called over damping. Critical damping is very good example is door closer. Our door closer is a critical damping. Okay, no damping is the ideal one. You take any system, always there is a damping. If air is also damping, air is also damping coefficient, viscosity, but very less. Oil has a more viscosity. Okay, now I will show what is the difference between damping and undamping. Okay. So, what is meant by undamping system and damping system? So, undamping means I will take a spring mass system, only spring mass system. I will take a spring mass system in vacuum as well as in air. Two cases I will take. Spring mass system in vacuum. In air. And here I will take in damping system. Suppose if I disturb this system in the vacuum, what happened? No air, no opposition, no resistance. It oscillates for a constant frequency, sustained frequency. It oscillates for sustained frequency. Constant frequency for 1 day, 2 day, 3 day. Because no, afterwards there is internal molecular frictional force, it will come to rest. But if you take in the air, so it starts for oscillating, it will come to rest after so many oscillations. X of t is what? And now it is oscillating with what? Both are oscillating with what? Omega n. What is the omega n value? Root k by m. Okay. But here there is a opposition. Damped. It is oscillating with not omega n. It is oscillating with omega d. Damped natural frequency. So this is the lesser than omega n. Damped natural frequency is equal to omega n root of 1 minus zeta square. For underdamping, I am talking about underdamping. Now, if you see the response curve or output curve, x of t displacement of the mass, so it will come to rest as early as possible because the damper is removing the energy in the form of heat to the atmosphere per cycle. Because in this case, mass is storing kinetic energy and spring is storing potential energy. These are interchanging the energy because once you pull the mass, then the potential energy is stored in the spring first. As soon as you leave it, the potential energy converted into kinetic energy into potential energy. But during one cycle, in the damper there is a oil, viscous oil. So it is incompressible. Then the temperature of the oil is increases. So the heat transfer to the atmosphere per cycle, it is removing the energy. When it removes all the energy, the mass will come to rest. Here the mass will come to rest as early as possible because there is a damper. It removes the energy. Here is a less damper. Here no damper. Here no damper. Is it right? So that these are you can understand the system underdamping, undamping and damping system. Okay, in the damping once again there are three systems. I will explain later. In the damping, it's called underdamping and it's called critically damping. Fine. And it is called what? Overdamping. I will explain further. Here basically I am underdamping system. I have explained underdamping. There is oscillations. Okay. So it is oscillating with omega n, it is oscillating with omega n, it is oscillating with omega d, damped natural frequency, radian per second. Here also radian per second. Here also radian per second. I hope you understood what is the difference between underdamping and damping. Today we have covered the standard form of second order system, C of S divided by R of S equal to omega n square divided by S square plus 2 zeta omega ns plus omega n square. This is called second order closed loop transfer function. And after that we have seen the zeta. Okay, zeta is opposition factor, and the correlation between zeta and C is equal to 2 zeta omega n m. So once I know C and omega n and m, I can find zeta. The third one is the different types of zeta: underdamping, critically damping, overdamping. Then the difference between undamping and damping. So in the next lecture we'll see the what is the poles. We'll see what are the poles as well as zeros and characteristic equation, how they are changing by changing the value of zeta. Okay, how the poles are moving if I change the value of zeta. In each zeta, what is the nature of the poles? Is it the poles are negative real with complex, otherwise pure complex, otherwise negative real with ripted? We'll see the mathematics behind the second order system. Okay, I hope you understood this lecture. Thank you.